Alright, so this is the formal definition. Let's look at one typical example. We have some vector field. Vector field has its subcomponents. So I'm working in Cartesian coordinates. So I have the x component, y component, and z components. But each component is itself a function of x, y, z. Right? Ax is space dependent. Ay is space dependent. Az is space dependent. So if I'm interested to find whether this vector field has a circulating component, I can form a closed loop. And that closed loop encompasses a surface. Once again, a surface in the language of vector analysis is a vector. So this closed loop is indeed a small surface. The direction points in the positive x direction. So that once the direction is pointing in x, you know its area must be defined by differential length in the y direction and z direction. Okay? So, in this case, I first want to evaluate segment number 1. So this differential surface has a closed loop defined by 4 segments. 1, 2, 3, and 4. And this surface is centered at x0, y0, z0. So this means if I want to know the net circulation over this closed loop, I have to calculate 4 times. I need to evaluate the circulation along segment 1, segment 2, segment 3, and 4. So what I'm trying to do is I want to evaluate the work done over segment number 1. So work on segment number 1. So this is your field making a dot product with differential length for segment number 1. So ask yourselves how to start. All you need to know is how to properly formulate the differential length in this case. So in this case, segment number 1 is pointing upwards, which means the unit direction is in the positive z direction. Positive z direction and with a length of delta z. So since for segment number 1, the unit direction is z direction, which component of the vector field is being sampled? Or which component of vector field A could give you work and could give you, therefore, could give you circulation? Can x component and y component really push you in the z direction? No. Because you're making an inner dot product. You're walking along the direction in the positive z direction. So the only potential being pushed by the field is by its z component, right? Az dot az gives you something non-zero. So you are essentially trying to evaluate the z component. How strong is the z component? Okay? So the work done by vector field A is only the z component multiplied by this differential length delta z. But the question is, this segment has its y position, having an offset. The entire surface is centered at x0, y0, and z0, but this first segment is having an offset in the y direction by delta y divided by 2. So this means, essentially, what I'm trying to evaluate, the work done along segment number 1 is the AZ component with its proper offset in the y direction and then multiplied by delta z. But this is not new. We know how to deal with it from last week. All we have to do is perform Taylor's expansion, right? So to properly evaluate this one, be careful. The AZ component, I want to evaluate the AZ component, but now the offset is in the y direction. So that means I need to evaluate, this is equal to the evaluation of AZ at the center point plus partial differential of AZ component, but in y. I want to know the slope of AZ component with respect to differential changes in y evaluated at the center point, but then multiplied by my offset in the y direction. And then the entire bracket is multiplied by the differential length, the total magnitude, delta z. As you can see, delta y multiplied by delta z gives you the area. Okay? So for the work done by the vector field along segment number 1, the only contribution is from the AZ component because your differential length is in the z direction. And it is this big. And that delta y divided by delta z is your unit surface area. That is your delta S. Okay, so as I mentioned, we need to evaluate the work done over 4 segments, 1, 2, 3, and 4. So at this point, which other segment do you want to calculate? Do you want to calculate segment number 2, 3, or 4? TA says, I want to calculate the work done by over segment number 3. Why? Because, as you can see, segment number 3 is also having similar direction in the z direction, but it's negative z. So these two can be directly compared, right? If you want to have circulation, 1 and 2 are orthogonal, they cannot be compared. But this one and this one, if they cancel, you have no circulation. If they don't cancel, you have net circulation. So the next segment I want to investigate into is segment number 3. So I want to investigate the work done by the vector field when I walk along segment number 3. So I walk starting from the top and towards the bottom. So in this case, dl is having a reverse sign. So now it's pointing in the negative z direction. Negative z direction. But the magnitude is still delta z. Alright? Now, of course, for the segment, it is offset negatively in the y direction by delta y divided by 2. So it's having a negative offset in the y direction. And our dl, differential length, is now pointing downwards. It's having a negative sign. So again, we perform Taylor's expansion. and we'll arrive at this formulation. So basically, the work done when you take segment number 1 is having a positive AZ, right? Plus a positive partial differentiation. As you take your segment number 3, the first contribution is having a negative sign. So W1, W plus W3 have this term being cancelled out, but essentially you have a non-zero term. So that tells you when you add the contributions of the works done over segment number 1 and 3, you do have potentially a non-zero result. So this is a point where you have to think. For this to be non-zero, your delta S is of course non-zero, right? You have an area. So the Z component in this case, when you make a partial differentiation to the Y direction, although it is a Z component, but it is a function of X, Y, Z. So your partial Y has to be non-zero in order to give a non-zero result for these two segments. So think about it. Let's come back to this. If this is your Z component, AZ, it is unidirectional, and maybe its magnitude is only Z dependent, right? For example, in this case, this is Z, Z. Just for example, your AZ component is in the Z direction, and its magnitude is defined by its Z position value. So in this case, your AZ making a partial differentiation to Y is 0. Therefore, there's no work done when you walk in a closed loop. Okay? So for conserved field, you only have a unidirectional field. You cannot have net circulation. Alright, so I don't want to repeat for the other two surfaces, but for each direction, if you want to find the net circulation, you have to form a closed loop. So total together, you have 3 differential surfaces, and you have to calculate or evaluate the works for a total of 12 segments. But for simplicity, everything you do should just conform to what you have learned, okay? So whenever you calculate the work over one direction, you would have one partial differentiation, right? So for the work done over 2 and 4, that would pick up AY making a partial differentiation to the Z direction. Why? You walk over segment number 2, you're walking in the direction of negative Y, right? You're walking in the direction of negative Y. But your offset is in the Z direction. So as you walk, you're trying to evaluate how much AY is having some circulating component, and you're making partial differentiation in the Z direction. Just take a look. You're walking in the direction of Y, positive Y, negative Y, but your offset as compared to the center is in the Z direction. So the Z goes to the partial differentiation. The direction is defined by your segment direction. So now, why do you have the negative sign? Why do you have the negative sign? Because for segment number 2, you're having a positive offset, but your direction is negative. Okay? As compared to this one, you have a positive direction and you also have a positive offset. So you have a positive sign. But whenever you have a positive offset, but then you have a negative sign, the entire derivative picks up a negative sign. Right? Okay, so eventually, this is something you learned in the past. If you want to perform a curl operation in Cartesian coordinate, you only have to write x, y, z unit vectors, partial differentiation, del x, del y, del z, and you write down the three components of the vector field, ax, ay, and az, and you just calculate the determinant. That's easy and straightforward, but the reason is, as I showed you, we can calculate the net circulation by the definition, and eventually it ends up in this very elegant form. But this is only in Cartesian coordinate. You can try to work on the other two coordinate systems on your own. Let me spend some time and talk about the generalized formulation. The definition of curl is trying to find the maximum net circulation. When you try to find the circulation, you need to make inner dot product of your vector field with the differential length. So when you're working in different coordinate system, differential length, if your unit vector is angular, your differential length dl is an arc, right? And then divided by differential surface. So take a good look at the generalized expression for curl of A. This is generalized. H1, H2, H3 are the Jacobians. For cylindrical coordinate, 1, R, 1. Spherical coordinate, 1, capitalized R, R sine theta. So take a good look for 30 seconds and ask yourselves why the generalized expression is formulated in this way. I'm using the colors red to represent red, blue to relate to the differential length. Differential length if your unit vector is angular. You are spanning an arc. So for example, you're working in cylindrical coordinate. In the d phi direction, your arc length is r d phi, so you have to multiply this Jacobian into it. Okay? Delta S needs to be divided. So H1, H2, H3 gives you the value. So you need to cancel out. Right? For this one, H1 is cancelled out, so you divide by H2, H3, meaning you have a surface. In the first direction, its magnitude is defined by the differential length in the second and third directions. So again, once you have a complete understanding towards the cylindrical coordinates, spherical coordinates, once you have an angular unit vector, it spans an arc. So that is the difference in H2 and H3. So you can use this formulation based on your understanding to the definition of curve. Right? So, are you okay on this? Students online? We still have 9 minutes. So, before I move on to Stokes' theorem, I want to make sure all the students are comfortable with what I covered? Any question from the audience? No? Not yet? Okay, so let's move on. Stokes' theory is very similar to divergence theory. From the definition that we just covered, curl operation is trying to evaluate the net circulation over a very small surface area. So this is working in a microscopic view. For example, I have a very big surface. But when I perform this curl operation, I'm asking myself, oh, do you have net circulation in a very small surface area? Meaning, I'm dividing my entire surface into many, millions of very small surfaces. And each one of them, do I have a non-zero circulation? But eventually, all that I care about, in the practical sense, is over the microscopic view. If each small area is giving me some kind of net circulation, I really care about what is the total circulation for the entire surface, right? So I can move my differential surface to the left-hand side, and then I perform integration for all the surfaces. That's what I'm doing now. I evaluated the net circulation for each differential surface, and eventually I want to add them all up. So I perform a total surface integration. Surface integration, two-dimensional. But Stokes' theorem is telling me, you don't really have to go all this trouble. If you want to know that result, you can simply evaluate the vector field, making a dot product with the closed contour. For example, this is a net, a fish net. So eventually I have the outer closed loop. So if I want to know the total net circulation for the entire net, all that I have to do is calculate the circulation on the outermost part, that closed contour. So again, this is reducing your work. You start with, initially you thought you have to perform surface integration, but it's downscaled to contour integration. So this is easy, and they would have the same amount. So how to understand it? How can these two be equal? Let's take a close look. So over this fish net, I divided into millions of small differential surfaces. For example, each surface is represented by 4 segments. When I try to evaluate the net circulation for this guy, right, I'm using my right-hand rule. So I'm evaluating the work just like I showed you. All the segments have a well-defined direction, right? For this case, all the segments are defined, so eventually they're working in a counterclockwise direction, so your thumb points outwards. But then the question is, for example, for this one, when I move to the surface adjacent to it, there would be one side which is common, right? But in this case, I still want to preserve the direction. So this segment, this very same segment, is taking on the positive sign when I evaluate for this differential surface. But when I evaluate the circulation for this surface, that same segment needs to point downwards. So So eventually they cancel out. So does this two. Cancel out, cancel out. So everything's being canceled. The only thing not being canceled is the outermost contour. Okay? So this is the physical meaning of Stokes' theorem. Instead of calculating a lot of components, the work done on the small segments that will be canceled out, you only need to evaluate the work done over the contour, which will not be canceled out. This is, in essence, having the same philosophy as divergence theory. So go back to the last class, go back to divergence theory, and ask yourselves, what are the differences? The meaning, the process are having the same meaning, where you can reduce the integration's dimension by a factor of 1, by an order of 1. But here, you're involved with curl operation. So essentially to me, in terms of mathematical approach, they are very identical, but they're trying to sense different fields. Here you're trying to evaluate the circulating field. For divergence theory, you're trying to evaluate the flowing out fields that flows out. Okay. All right, so I should stop here. Let's take a 10 minutes recess, and then we can come back. So for the next class, we are going to finish vector analysis, and we will move on to electric field, finally. All right, let's take a rest.